Chapter 10, Section 1, Tangents to Circles. First thing we need to define is a circle. A circle is the set of all points in a plane that are equidistant from a given point. That given point is going to be called the center. The distance from the center to a point on the circle is the radius. Two circles are congruent if they have the same radius. I'm kind of going quickly through these. All of these definitions should be something that you're familiar with. So that's kind of why I'm going through. If you're not sure what all of this means, if you don't know what a radius is, etc., then you need to look that up somewhere else. The distance across the circle through the center is called the diameter, which is 2 times the radius. Here I have a circle, and for this circle, this point would be the center. The radius would be any line, and there could be several radii drawn here. Any line that connects the center to another point that is on the circle. And then the diameter is going to go all the way across the circle. Again, make sure that it's going through the center. Some new vocabulary. It says a chord is a segment whose endpoints are endpoints on a circle. The diameter would be one example of a chord. A chord does not have to go through the center of the circle, though. A chord is just going to be a segment whose endpoints are on the circle, not necessarily going through the center of the circle. A secant is a line that intersects a circle at 2 points. So a secant is very similar to a chord, but now a secant is going to be a line, which remember a line is going to extend in 2 directions. It's going to be a line that intersects the circle at 2 points, but it doesn't have endpoints on the circle. And then a tangent is a line that intersects a circle at 1 point. Again, I have a circle. This blue segment would be considered a chord. Notice that it ends at on 2 points that are on the circle. This orange line would be considered a secant. Notice this time it's a line that's extending through the circle, and again, it's intersecting at 2 points. And then a tangent, remember, it's going to intersect at just a point. So I have this yellow point, and then this yellow line would be tangent because it is only touching the circle at that 1 point that's shown. This first example says, tell whether the segment is best described as a chord, a secant, a tangent, a diameter, or a radius. A diameter is going to be more specific than just a chord. A diameter would be a chord that goes through the center of a circle. So if it's a diameter, we want to call it a diameter, but if it's just a chord, we're going to call it just a chord. A asks us to tell what segment AH would be. AH would be a line that is tangent to my circle. B asks us what EI would be. That's segment EI. Segment EI would be the diameter because it goes through the center C of the circle. DF is a segment with 2 endpoints on the circle. It does not go through the center, so it would be considered a chord. And then CE, C is the center of the circle, and then E is a point on the circle, so CE would be a radius. If you look, the only word that we haven't really defined here is the line that would be secant. An example of a line that would be secant would be HG. Notice it goes through the circle, through 2 points on the circle, and it's extending in both directions. 2 coplanar circles can intersect at 2 points, 1 point, or no points. Circles that intersect at 1 point are called tangent circles. Two circles that have a common center are called concentric. Notice in the example on the left, I have two circles. I have a smaller circle inside of a larger circle, and they're sharing a center. But then if you look at the circle on the right, it looks like there's just one circle there, but technically there could be two circles. They would just be congruent circles that are on top of each other. Two circles can have either internal or external common tangents. So remember, a tangent is going to be a line that intersects a circle at one point. Two or more circles can have a common tangent when that line is going to intersect both circles at just one point. An external tangent example would be I have two tangent circles, and then that orange line would be tangent to both circles. It's intersecting the circles at the point where the circles intersect. Notice external, this tangent line is not cutting between the two circles. It's kind of on the exterior of the two circles. And then that would be another example of external tangents. Notice again, these lines aren't really cutting in the space between the two circles. It's kind of on the outside. So those would be external tangents. Internal tangents, we could have one example here. I would have tangent circles again, but this time notice that the tangent line is cutting between the two circles. And then another example of internal tangents, I could have that same two circles, the second example for external, but this time my tangent lines are going to be cutting the space in between the two circles. So those would be internal tangents. They're going between the two circles. This next example says, tell whether the common tangent is internal or external. This looks a whole lot like one of our examples that we just had. This tangent would be external. For segment CD, it's kind of weird. What they've done there is they've connected the two centers of those circles. So that's what CD is. But the tangent line that we're talking about would be on the bottom left-hand side of that diagram. This next example says, give the center and radius of each circle, describe the intersection of the two circles, and describe all common tangents. First thing they ask us to do is give the center and radius of each circle. So if we look at circle A first, notice there what I've done is you can name a circle based on the center, what the center is named. So the center of that first circle on the left side is point A, so we would consider this circle A. Circle A has a center at 2, 2, and if you count the spaces from A to a side of that circle, you would find that the radius would be 2. The center of B would be at 6, 2. And the radius for circle B is also 2. So what we know about these two circles is that they would be congruent circles because their radii have the same measure. It asks us to describe the intersection of the two circles. Notice that circle A and circle B are intersecting at one point. They're intersecting at 4, 2, and which would make these two circles tangent circles. They intersect at exactly one point. And then they also ask us to describe all common tangents. The common tangents that circle A and circle B would have would be the x equals 4, the line x equals 4, that would be that line that is vertical cutting between the two circles. So it would be considered an internal tangent. And then the other common tangent, remember common tangent means that it needs to be a tangent to both circles that we're talking about. The other two common tangents would be y equals 0, which would be the x-axis. If you look at that blue line, the x-axis, that would be tangent to both circle A and circle B. And then y equals 4, which would be the line horizontal above the two circles. Both of those would be considered external tangents. Some theorems that we need to talk about. The first one is, if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So if we have this circle and we have a tangent line, what we should be able to do is we should be able to draw in the radius to the point of tangency, and those two lines should intersect to form a right angle. If they do not intersect to form a right angle, then it would not be a tangent line. In a plane, if a line is perpendicular to a radius of a circle at its end point on the circle, then the line is tangent to the circle. So basically what we've done is we've taken our last statement and we've kind of rewritten it a little bit. So this time, if a line is perpendicular to the radius of a circle at its end point, then it's going to be a tangent line. This first example says, is CE tangent to circle D? And explain. Notice we have a tangent line, or what we think is a tangent line. We're not quite sure, CE. But notice that they tell us that the radius is 11, and then they also give us this segment DC is 45. If this segment CE is tangent to circle D, then we know that angle E should be a right angle. What we can do based on the information that they've given us is we can go ahead and see if triangle DEC created by the three segments is a right triangle. And if it is a right triangle, then angle E would be the right angle because it's opposite of my longest side. So what I can do is I can set it up, and I can say, we're going to use the Pythagorean theorem. I can say 11 squared plus 43 squared equals 45 squared. Technically, we don't know that it's equal right now. That's what we're trying to figure out. We can say 11 squared is 121. 43 squared is 1,849. When we add them together, they do not equal 2,025, which is 45 squared. Because the Pythagorean theorem is not true, we know that this is not a right triangle, which means angle E is not a right angle. So based on that information, we can say that segment CE is not tangent to circle D because it does not form a right angle with its radius DE. This next example says you are standing 14 feet from a water tower. The distance from you to a point of tangency on the tower is 28 feet. What is the radius of the water tower? The information that they've given us is pictured in the diagram. Notice here we have BC is 28 feet, but then we have the radius AB is R. And then we have that segment AC is 14 feet plus the radius R. What I need to do is I need to set up the Pythagorean theorem. R plus 14 would be considered the hypotenuse. So we're going to have R squared plus 28 squared equals R plus 14 squared. If you remember multiplying binomials, we can use the FOIL method on R plus 14 squared. Remember, FOIL is an acronym standing for multiplying the first, outside, inside, and then last terms in your binomials. R squared is going to remain R squared. 28 squared is 784. And then R plus 14 squared is R squared plus 28R plus 196. When I need to combine my like terms, I would subtract R squared from both sides, and when you do that, they're going to cancel out. I also went ahead and subtracted 196 from both sides to get 588 equals 28R. The last step would be to divide by 28, and when you do that, you get 21 feet for R. So the radius of this water tower would be 21 feet. The next theorem says if two segments from the same exterior point are tangent to a circle, then they are congruent. So here I have my circle, and I have points A, B, and C. I'm going to have the tangent, a line tangent to the circle AB, and then I'm also going to have a line tangent to the circle BC. What this says is that because these two lines are tangent to the same circle from and they intersect at point B, I can say that segment AB would be congruent to segment CB. This next example says AB is the tangent. Segment AB is tangent to circle C at point B. And then AD is tangent to circle C at D. Find the value of x. Notice we have two tangent lines, AB and AD, intersecting at point A. And they tell us that the lengths of them are AB is x squared minus 4 and AD is 21. Because these two lines are tangent to the circle and they intersect at point A, we know that the segments created would be congruent, so we can set them equal. So I'm going to have x squared minus 4, which would be the length of AB, equal to 21, which they tell us is the length of AD. Go ahead and add 4 to both sides and you get x squared equals 25. The inverse of squaring x would be to take the square root of both sides, which gives you x equals 5. Or x could also equal negative 5, because remember the square root of 25 would be both a positive and a negative. 5 times 5 is 25. Negative 5 times negative 5 is 25. Today's assignment is on page 599. It's numbers 2 through 16 even, and then numbers 18 through 48 all.